Welcome to physics class today. I am Julia Alalibo, and I'll be taking you on the theme, interaction of matter, space, and time. And the topic for today is a very easy one. It's position, distance, and displacement. Before we go into the lesson, let's look at our objectives for this lesson. By the end of the lesson, you should be able to explain position, distance, and displacement. Clearly differentiate between distance and displacement. Use the Cartesian system to locate the position of the object on the XY plane and solve major questions on distance and displacement. First off, we start with position. Now, we use the word position every day, even if we don't know about it. You always ask somebody, where are you? What's your location? You are indirectly asking the person, what is your position? Position refers to the location of an object with respect to its frame of reference. The location here refers to the distance and direction, while the frame of reference refers to the origin or starting point. That is to say, your frame of reference is your point of view. In English, when you talk about frame of reference, you just mean the person's point of view. But in physics here, we use a frame of reference known as the Cartesian plane. So when I'm talking about position in physics, and I talk about frame of reference, I mean your Cartesian plane, which has the origin or the starting point. Position is a vector quantity and therefore has both magnitude and direction. Now you may be wondering how someone's position actually has a direction. Let's take an instance. A class of 37 students, with a student taking 37th position in the first term and then taking 23rd in the second term and 15th in the third term. We can use a line to illustrate this. We have a class of 37 and then number 1 is the highest position we can get in a class. First time he took this position. And then later on he progressed to take the 23rd position in the class. And finally in the third term he came 15th. Now these are his various positions. And as we said before, that position is a vector quantity. It has a magnitude and also has a direction. We can see that the direction of the student is an upward one. He moves from 37th to 23rd and then to position 15. There is an upward direction of the position, which means that position is a vector quantity. And remember we said that position has to always be in a frame of reference. For this particular student, the frame of reference is the class of 37. For instance, some schools, they grade you based on different subjects. Let's say in physics, this same student came, in first term, he came 15th. And then in second term, he came 10th. And then in the third term, he came 5th. Now, this is his position in physics. So with respect to the frame of reference, physics subject, he came 15th, 10th, and finally 5th. So because the frame of reference has changed, that means his position has also changed. But the overall class, he came 37th, 23rd, and 15th. This is just to buttress the point that position must have to do with a particular frame of reference. In physics, as I said before, we use the Cartesian plane, which is an x and y axis, to demonstrate the frame of reference of a particular position. To explain position further, let's consider a boy playing with a football. He kicks it away from its initial position towards the goal post. It is northeast of his position. This indicates that the new position of the ball has a direction, northeast. Now, this is the original position of the ball. If you use a cardinal point, we know that this is the north, the south, the west, and then the east. And he kicks the ball this way. We can see the direction of the ball. It's in the northeast direction. This is the present position, and this is what we care about. We said before that position is a vector quantity. So this ball here, it has a magnitude, and then it has a direction with which the ball moved. It's in a northeast direction. Moving further, to use a mathematical example to explain this, I said before that in physics, our frame of reference is usually a Cartesian plane. A Cartesian plane is a plane that is used to explain the position of an object. But for this first example, we are just going to use the x-axis. In a one-dimensional plane, a straight line known as the x-axis can be used to define the position of an object. Now, this is the straight line we have here. This is a ball right here, and this is a triangle right here. We can see our number line. This is the origin. As I said before, this is for this particular horizontal line, this is the frame of reference with the origin or reference point at 0. And we know how we do our number line. Number it 1, 2, 3, and so on. While anything to the left of the 0 is a negative, -1, -2, and so on and so forth. So the position of this ball is on position 3, while that of the triangle is on position -4. Because as we said, to the left of the 0 is a negative, while to the right of the 0 is a positive. You can either write it as 3 or +3, knowing that when there's no sign, it indicates that it's a positive value. So the position of this circle is actually +3 of the origin, while the position of the triangle is -4 from the origin. So these signs, the plus and the minus, gives us the direction of the ball and the triangle respectively. Now moving on to a two-dimensional plane. That is, this is the actual Cartesian plane where you have your x-axis right here and your y-axis right here. The vertical axis is the y-axis, while the horizontal is the x-axis. Now we are asked to locate point A, point B, point C, and point D. Locate their positions in this Cartesian plane. Point A has the coordinates 2 and 5. 2 is on the x-axis, while 5 is on the y-axis. So what do? Having drawn our Cartesian plane, with this as the origin, our reference points, we count 1, 2 for point A. So it's somewhat here. Y is on 5 on Y, somewhere here. So this is the location of point A. But that's not all. As we said, position is a vector quantity. You have to say the direction of point A. So point A is in the direction. You draw your cardinal points. This is your north, your south, your west, and your east. So we can say point A right here is in the position, is in this position, and is in the direction northeast from the origin. Then taking a look at point B, the x-axis is 3, while that of the y-axis is -4. 3, we know right hand is positive, left hand is negative. For the y-axis, upper side is positive, while the lower side is negative. We have 3 here. You can just draw dotted lines. And then point B is on -4. So it goes this way, +3 and -4. Again, you use your cardinal points. This is in this direction. And we know these are south, these are east. So point B is in the position, B is in this position and in the direction southeast. Now point C, the coordinates given are -2 and -3. We have it here, this is -2, and now -3 is somewhat here. So you try to trace a line that joins both points together. And to do this, this is what we get. This is point C. And this is the position of point C, but for a vector quantity, it needs to have a direction. We come back to our cardinal point. Point C is in the point southwest of its position. And then finally, we look at point D. We have -5 and we have 1 on the y-axis. So you try to look for the intercepts where they do intercept. And if you draw dotted lines up to here, you see that this is the location of point D. And using your cardinal points again, point D is in this position and its direction is northwest. So with this, we've been able to see that position is actually a vector quantity. One other instance, where I'm standing in front of this board, I can say I am 2 meters in front of the board. That is my position. It has the magnitude, maybe it's 2 meters from the board, and then the direction is in front. If I were to be behind the board, you use the word behind to indicate direction, and that's negative, while for front is positive. So on to the next one, we have distance. Distance is simply how far has an object traveled, or how much ground has been covered by an object. It is defined as the length of the path traveled from the origin to the final destination. Distance has to do with your total movement of the actual path traveled by an object or by a person. Distance is a measure of how far an object has traveled, regardless of the direction the object traveled. Distance is one that does not have to think about the direction. That means it's a scalar quantity. Remember, the definition of a scalar quantity is one which has magnitude but no direction. And the unit of measurement for distance is in meter. We measure distance in meter as the SI unit. Other units could be used, but for today we are going to be using meters as the SI unit for distance. Let's look at the first example to illustrate distance. Using the figure below, a boy moves from point A to point B to C to D and back to A. What is the total length of the path traveled? Now this is the diagram to illustrate this. He moved from this point in this direction to point B and then moved to point C in this direction, went back to D and then back to A. Now the question is, what is the total length of the path traveled? And as said earlier, distance is the total length of the actual path traveled. So it's quite easy. All you have to do is a summation of the entire length of his movement. You have distance here is equal to the length of this AB plus BC plus CD and then plus DA, which gives us is 10 plus 5 plus 10 and plus 5 gives us a sum of 30 meters. This is the distance the boy traveled from point A back to point A. Is the total length of the entire path traveled by the boy. Now, one more example. Assuming a man jogs from point A to point B and then turns around and jogs to point C, what is the distance traveled where each unit represents 100 meters? Now, this is a quick illustration of what he did. The man started from this point and jogged all the way to point B. On getting to point B, he turned around and came back to C, right here. So the question is, what is the distance traveled by the man? So the first distance is AB, which is this, AB, plus BC. And he said each unit represents 100 meters, meaning from this point to this point is 100, this to this is 100, and so on. So to count the number of meters in this point A to B, you count 1, 2, 3, 4, 5, 6. That is 600 meters. While from B back to C is 300 meters. Distance is simply the summation of the entire distance covered, the total path he traveled. So his distance covered is 900 meters from his initial point to his final point C. Another example here says, using the figure below, assuming a boy moves from point A to C through B, what is the distance he traveled? He went this way and then came back this way. His distance, as we said earlier, is simply the summation. You simply do AB plus BC, which gives us a distance of 20 meters. And then, this is the last example we'll be having for distance. Using the figure below, assuming a boy moves from point A right here to point B via the winding route, the distance covered can be calculated by simply summing the length of each path taken. So, as we said in the question, he went through the winding route. So he came this way, and then this way, and this way, and this way, and all that, until he got to point B. Now, the distance traveled is the total length of the actual path traveled. So you do this, and from the question, you can see that this, from this point to this point, is 20 meters. So this is 1 point. He went this way, 20. He went another way, 20, came back 20, and so on. And if you count the number of turns he made, it's about 8 turns. So you just do a summation of the 8 turns to give you 160 meters that he traveled so far. That's the total distance he covered to get to point A to point B through the winding route. Now, we've said a lot about distance. Why don't we look at displacement? Let's take a look at what displacement means. It means how far out of place an object is and in what direction. Displacement is gotten from position. We said earlier that position is a vector quantity, and displacement here talks about how far out of place and in what direction. So displacement is defined as the distance traveled in a specified direction. When we're talking about distance, we just said it's the distance traveled. We don't want to know if he went left, right, whatever, up or down. We just know how far he traveled. But in displacement, we talk about the distance traveled in a specified direction. is the shortest distance between the origin and the destination. Displacement is concerned with your initial and final. If you got to your final without branching, it doesn't care. If you got there with branching, it still doesn't care. All it wants to know is that you have an initial position and then you got to a final position. It's a vector quantity because both magnitude and direction are components of displacement. In displacement, if the origin or the starting point and the final point are the same, then the displacement is 0, because we said displacement only cares about your initial position, your origin, and then your destination. It doesn't care if you have to go through routes to get to your destination. It only cares about the origin and the destination. But if the origin and the destination are the same, your displacement is 0, because it's the distance, shortest distance between the origin and destination. The SI unit of displacement is meter. Now, some few examples to illustrate this. We are going to be using exactly the same examples we use for distance to illustrate displacement. Now, from this example, a boy moves from A to B to C to D and back to A. What is his displacement? We said displacement is the shortest distance between the origin and the destination. He moves along this path. He moves from this A to B, B to C, C to D, and then D to A. But he arrives back at his original destination. Displacement is the difference between your final destination and your original destination. That means that the boy did not have any displacement. His displacement is 0 meter or 0. He didn't change position at the end of the day. He came back to his initial position. That's why we said before that if your origin and destination are the same, that means your displacement is 0 because there is no change. But if we were to calculate distance, as we saw earlier, the distance for this particular movement is 30 meters. Now, another example to illustrate displacement. Assuming a man jogs from point A to point B and then turns around and jogs back to point C, what is his displacement where each unit represents 100 meters? So he started from this point, this is point A, went all the way in this direction to point B, and then for whatsoever reason he decides to turn back to point C in this direction. Now the question is, what is his displacement? We can solve these questions in two ways. We're going to solve it with the first example. Now he started from his initial position is AA, which is the 2 meter mark, and we said each unit represents 100 meters. So this is actually the 200 meter mark. While his final position, as we said earlier, displacement doesn't care where you branch to. It just cares about your original and your final. His final position is point C. On this number line, it's actually 500 meters. We don't want to know if he went to B or not. All we know is that he stopped right here. So the displacement is 500 meters minus 200 meters to give us 300 meters. And we said also too that displacement is a vector quantity. You can't tell me the displacement of an object without telling me its direction. The man moved in the direction towards the right of A. This is the right of A. So his displacement is on point C, the difference between C and A. So he moved 300 meters to the right of A. This is his displacement. We can also solve it a second way by doing this. Initial position, final position. This is irrelevant to displacement. We don't want to know what he did here. You just say the final position. You assume this is your 0 mark, right? This is your 0 mark because this is where he started from. You just call it point 0. And 5 here, we said the question made us understand that each unit represents 100 meters. So this is 100, 200, 300. So displacement is final position minus the initial position, which gives us 300 meter mark right here, minus the 100 meter. So displacement is final position minus initial position. So his displacement is actually 300 meter minus the 0 meter mark, which gives us 300 meter towards the right of A. Displacement always has a direction. Now moving on to another example. Using the figure below, assuming a boy moves from point A to point C through B, what is his displacement? Now, this is the initial position, this is his final position. He went this way, he went from point A to point B, and then to C. But we said displacement is the shortest route from the origin to the destination. He went this way, but he could have just gone this way. Distance is the actual path taken, but displacement is what is the shortest route from your origin to your destination. So the boy went this way, but he could have as well just gone this way. So to calculate displacement, you calculate the distance from A to C without getting to B. But now we cannot just use algebraic methods because this gives us a right-angled triangle. And this right here is the hypotenuse. You use Pythagoras' theorem to solve this. And we know that Pythagoras' theorem says the hypotenuse squared is equal to the adjacent square plus the opposite square. This is the hypotenuse, while this right here is the adjacent and this is the opposite. So you make a summation. AB square is 15 square and BC square gives us 5 square. The square root of the summation of both of them gives us a square root of 250. That means AC is 15.81 meters. As I said, you can do your cardinal points to know the exact direction of this boy from A to C. This is the north, the south, the west, and the east. And his direction is this way. If this is our A here, our C is here. So his direction is 15.81 meter in a southeast direction. Now, this example we use to solve distance. Using the figure below, a boy moves from point A to point B via the winding route. What is his displacement? He wanted to move from his origin to his destination, right here. And he went through these routes, the curved routes or the winding routes. Nobody knows why he refused to just go straight. Maybe there's no path connecting A to B. But displacement, as we've said earlier, is the distance, shortest distance from A to B, from your origin to your destination. So if this is a 100-meter walk or distance, his displacement is 100 meters in the direction AB, and AB is to the right. So his displacement is 100 meters in the direction AB, irrespective of the path he took. And then we are going to look at some subtle differences between distance and displacement. We said distance is the total movement of an object regardless of its direction. But displacement is the change in position of an object with respect to its direction. We always want to know where, in displacement, we always want to know where did it go and what is the direction it took. And it's also the shortest route from the origin to the final position. We said distance is a scalar quantity, while displacement is a vector quantity. It takes direction into consideration. And distance is always positive, but displacement may be positive, negative, or zero, as in the example we saw before, where the guy returned back to his initial position, making his displacement zero. Positive when he actually leaves towards the right of his direction, and negative when he moves towards the left of his direction. But distance is always positive. It can never be negative because it's a summation of the length or the path taken to get to his destination. Now, in summary, let's have a look at what we learned so far. We said position is a vector quantity which describes the location of an object with respect to a frame of reference. And distance is a scalar measure of the actual path an object traveled. Displacement is a vector measure. It takes magnitude and direction of the shortest path traveled by an object from its initial position to final position. The distance traveled by an object is always greater than or equal to the magnitude of the displacement. We said magnitude here because magnitude refers to just the size of the object, the distance traveled by an object is always greater. It cannot be less than the displacement because distance is a total of the actual path taken. It could be, it's always greater or equal to the magnitude of the displacement of the same object. The SI units of position, distance, and displacement is meter. Now, to test our understanding of the subject, we are going to look at two examples, two questions to know how well we understood this topic. Elizabeth drives 30 kilometers west to visit her grandparents and then back drives 40 kilometers east to her parents' house to stay for the weekend. Calculate her distance and displacement respectively. Now, this is what happens. The options are A, 70 kilometers, 10 kilometers west, B, 10 kilometers, 70 kilometers west, C, 70 kilometers, 10 kilometers east, and D, 10 kilometers, 70 kilometers east. Now, this is Elizabeth's, let's say this is her origin. She drives 30 kilometers west, so she goes in this direction, 30 kilometers, to visit her grandparents, and then back drives 40 kilometers east to her parents' house to stay for the weekend. So this is her present position. And then she decides to go back 40 kilometers to her parents' place. So she goes this way, covers the 30-kilometer mark, and then adds some more 10 kilometers to her parents' place. So this is 30 and this is 10. So she goes 30 kilometers from her starting point to the west and then goes back 40 kilometers to the east. Now calculate her distance and displacement respectively. Her distance is a sum of the total paths traveled to get to her destination. So she does, the distance can be calculated as 30 kilometers, that's this here, plus the remaining 40 kilometers to give us a distance of 70 kilometers. Then for her displacement, displacement is your final position minus your initial position. This is her initial position, the 0 mark here. And finally, at the end of the day, after visiting her grandparents and her mom, she ends up here on this position. This is 10 kilometers from her origin. We don't want to know if she went to her grandparents' house or came back to her own parents' house, but the difference between her origin and her final destination is 10, meaning that her displacement is 10 kilometers to the east, because this is the final position and this is her original position. So her displacement is 10 kilometers to the east. And where do we have that? We have 70 kilometer distance and 10 kilometer east. Therefore, option C is the correct answer. She traveled 70 kilometers by distance and 10 kilometers east by displacement. The last question for this lesson: what is the similarity between position, distance, and displacement? A, they are scalar quantities. B, they are vector quantities. C, they all have direction. And D, they all have magnitude. Now, option A says they are scalar quantities. That means position, distance, and displacement are scalar quantities. Is that correct? No. Because the only scalar quantity amongst the three of them is distance. Option B, they are vector quantities. That is also incorrect, because only position and displacement are vector quantities. C, they all have direction, which is also very wrong, because position has a direction, distance does not have a direction, and displacement has a direction. The fourth option says they all have magnitude, and this is the correct answer right here, because position has magnitude, distance has magnitude, and displacement also has magnitude. So if you chose option D, you are very correct. We've come to the end of our lesson on position, distance, and displacement. I hope you had a nice time. I understood the lesson as well. Let's do this again some other time.